So our next concept within matrices that we want to talk about are determinants, and we'll see how to find determinant solutions of linear systems. So to begin, we're going to start with what is a determinant. So every n by n matrix, and this is super important, it's the same number of rows and columns, it has to be a square matrix, is associated with a real number called the determinant of A. It's denoted by two different things. You can full on write determinant DET of A, or the easier way is to put A inside a set of absolute values, okay? So you'll see this pretty common if you move on to trig, move on to calculus. A lot of times it's a representation for a norm, which is a very specific concept. So it's a real number that's associated with all of our matrices, okay? So we're gonna go through how to find determinants, specifically 2 by 2 and 3 by 3. The concept for 3 by 3 extends to 4 by 4 and 5 by 5 and so on. But it is a little bit more complicated the more or the bigger you get. So we're only going to be focusing on 2 by 2 and 3 by 3 because that's the kind of systems we've been solving. 2 equations with 2 unknowns, 3 equations with 3 unknowns. So 2 by 2 is definitely the easiest. If we have a matrix A, which has 4 different entries, then the determinant of A is found by doing the following. So we have our entries A, B, C, and D. Remember to take a determinant. We change those brackets or parentheses to straight lines. What we're going to do is we're going to take the product of that main diagonal. So the determinant will equal A times D. And then we're going to subtract the off diagonal or the backwards, which is B times C, okay? You'll see this pattern is going to appear a lot, especially when we get to 3 by 3s, the same idea is going to happen. Positive is considered this diagonal, negative is this backwards diagonal. So to show you with this particular matrix, if A has the elements 7, 2, -1, and 4, then when I go to find the determinant of A, again, we change those brackets to absolute values, straight lines. We take the product of the main diagonal. So this would be 7 times 4. And we subtract the off diagonal, which is 2 times -1. So 7 times 4 gives me 28. 2 times -1 is -2. So subtracting that becomes plus. The determinant of this matrix is 30. Okay. So again, this just gives me one number that is important and associated with this matrix. Now, when we're doing 3 by 3, we're going to start by talking about something called cofactors. So we write determinants of larger matrices in terms of smaller ones using a cofactor expansion. So even when I get to higher levels, your goal is to eventually write it into matrices that are 2 by 2, okay? So each spot in your matrix is designated with a sign, positive or negative, in the expansion. So to show you that, what I'm going to do is indicate what these elements look like. If we have a 3 by 3 matrix, we would have 3 things in each row and column. So the way we're going to indicate this is with a subscript. We have the first row. So remember, it's an M by N. The row always goes first. So then we have our next row, it would be row 2, and then we have row 3. But then I also need to indicate the column. So this is column 1, column 2, column 3. So we indicate that with column 1, column 2, column 3. Then this corresponds to a matrix of signs, whether it being positive or negative. So you'll see the diagonal always has the same elements in the first and second because it's 1, 1, 2, 2, 3, 3, 4, 4. It is in that center position. So the way you can actually figure out the signs is you add these together. If it's even, it's positive. If the two numbers add together and are odd, then it's negative. But really it just kind of creates a pattern. So 1 plus 1 is 2. That first position in the first row, first column corresponds to a positive expansion. Then if I move on to the next one, it's 1 plus 2 is 3. That's negative. So this would be negative. Really what's happening is it's going to increase by 1 each and every time. So now this one is 1 plus 3, which is 4. That turns back to a positive sign, okay? So ultimately you're gonna get alternating patterns. 2, 1 added together is 3, so it's negative. 2 plus 2 is 4, so this sign will be a positive. And 2 plus 3 is 5, so that is negative. And then following the same pattern, you'd get plus, minus, plus. It's always going to alternate, okay? So the way we do a cofactor expansion is, say I want to expand along this first row. I'm gonna take this number out, attach that sign to it, and then I ignore everything in that row and column, and that leaves me with a 2 by 2 matrix, okay? And then we're gonna do that for every element in that particular row, or you can expand along a column. So before we do that, I just wanna get to what is the cofactor of a specific row. So we're gonna try to find the cofactor of A, 2, 1. So that means the second row, the first column. So that would be this element here. So we indicate this as the cofactor with the C, C2, 1. Okay. If I look at my sign matrix, that would be a negative quantity. So we get a negative attached out front. Then I pull this number out as well. And then I'm going to be left with a 2 by 2 matrix. Okay. And let's go ahead and turn these into black. The way I find what's left in the 2 by 2 is I ignore everything in this row and this column. Okay. So my numbers that are left are -3, -2, 0, and 2. Okay. So again, you take the sign from the sign matrix, you pop out the number in that position, ignore everything in the same row and column, and then you take the determinant of the numbers that are left. So from here, that minus minus turns to a positive 1, and then I want to times it by the determinant of this 2 by 2. So I multiply that main diagonal, and then I subtract the multiplication of the off diagonal. So thankfully 1 times anything is 1. So this is -6 minus 0. So this cofactor is -6, okay? So to find my determinant, what I would do is I would continue to do this along that row and column, and you just add those values together. So then I would have to find the cofactor of this element. So this would be positive. Then I pull out the -4. I would ignore everything in that row and column, and then find the determinant of the numbers that are remaining. Then I would have to do the same thing for that final position. So let's try with this exact matrix. We're going to find the determinant of A by expanding along the first row. So we're going to use the cofactors of these 3 elements. Okay. All right, so let's go ahead and start by just copying this matrix. And again, we're taking the determinant of A. So we've got 2 negative. So multiplying those together gives us a big ol' 0. Okay. Now I want to subtract all of the off diagonals. So starting with this first one, that is -1 times -4 times -2. So that gives us -8. Next diagonal is 0, -3, 2, which gives us another big ol' 0. And then our third one, which I'm going to have to squeeze in at the bottom here, you get 2 times -1 times -3, which ultimately gives us a positive 6. So -16 minus 9 gives us -25. And then here, -8 plus 6 gives us -2. -25 plus minus minus turns to +2. We end up with -23. So exactly the same determinant, but I definitely think much cleaner to go through, okay? So I would highly recommend using this method for 2x2 systems instead. Now, because these are a new operation, we do have some properties that can help us out. So if we think back to our elementary row operations, we know we can do them and it doesn't change the solution to a system, but it could potentially change the determinant. Doesn't always though. And then also there's going to be some easy ways to kind of immediately figure out what a determinant is based on what it looks like. So we're going to go through all of our different determinant properties. If there is a row or column of zeros, immediately you don't have to do anything. The determinant is going to be 0. Because it comes back to this. If you have an entire row of zeros, then no matter which forward or backward diagonal you look at, it's going to be multiplied by 0, it's 0. Okay. If you swap 2 rows, it's going to change the sign of the determinant. So if it was positive, it switches to negative or vice versa. If 2 rows or columns are identical, then again, immediately you're going to know that the determinant is equal to 0, okay? Basically, if those 2 rows are identical, it's going to guarantee you that you get a row of zeros when you do those row operations to cancel out and get zeros below it. So immediately you're going to be in that case, you have infinite solutions. Your determinant is going to equal 0. If you add a constant multiple of one row to another row, like we did to do the Gauss-Jordan elimination, that is not going to change the determinant at all. And then if you have a matrix in triangular form, what that's going to mean in order to calculate your determinant is you just multiply the stuff on the main diagonal. And to show you what triangular form is, basically you could have one of two things. We'll look at that 3x3 case because the 2x2 case is really boring. But triangular form means you have elements on your main diagonal. They could be 0, but you have elements on the main. Upper triangular means you have numbers, not all being 0, in the upper spot, but you have a triangle of zeros in the bottom. So to find the determinant, you just multiply the 3 things on the main diagonal. Lower triangular form means you have elements in the lower half. And then you have a triangle of zeros above that. So same thing again, you just multiply the stuff on the main diagonal. Okay. So these properties are just helpful because if we know something, it's much easier than having to go through the tedious process of finding the full determinant. If it's got a nice form, utilize that. So let's try a few examples. We're going to find the determinant of the matrix. So starting with A, I could definitely just jump into doing this. However, I see right here, I have an entire column of zeros. So without doing any work, I immediately know this is equal to 0. And so again, just to show you, I can do this pretty quickly here. If I were to calculate this determinant, I copy the first row and second column again. What happens is, if I look at the forward, I have a 0, I have a 0, I have a 0. All of those multiplied will be 0. And then if I go the backwards, every single one of these also has a 0. So their product will be 0. So without doing any work, when I've got that row or column of zeros, the determinant is 0. For the second one, if I look in here, I have a triangle of zeros. So to find my determinant, I just go ahead and I multiply the main diagonal. So this is a triangular matrix. Again, this is called a lower triangular because all the elements are in the lower part. So all we do is we multiply those diagonal elements. So this determinant, without having to do everything, is 7 times 6 times 4, which would give us 168. Okay. Again, the reason for this is not too bad, so let's do that just right here to show you real quick. But it's kind of similar to the first example. What happens is when I go to multiply, those give me the 168, but then you get 0 and 0. When you look at the backwards, you have 0, 0, and a 0. So really the only thing that ends up staying is that first main diagonal. Okay. Looking at this next one, we're going to use the fact that this determinant is equal 3 to evaluate the following. So if I look, well, this is my first row. It's now moved to my second, and my second has moved to my first. So here, 2 rows are switched. So all that happens is the sign needs to change. So instead of it being positive 3, the determinant of this matrix is negative 3, because it's just shaking up the order of those forward and backward pieces. Okay. The hardest one to kind of identify is going to be when you add a constant multiple of one row to another. That one's not so clear cut to try to figure out, so you might not recognize it, but that's okay. Just go ahead and you can find the determinant. They're not bad once you use this forward and backward diagonal situation. Okay? So now that we have some familiarity with determinants, we're going to talk about how we can solve linear systems utilizing them. And this is a concept known as Cramer's rule. And again, instead of having to go through and use Gauss-Jordan elimination, we can talk about the determinants of matrices to get our solutions. So I'm going to start with a 2 by 2 matrix and then show you how the idea extends to 3 by 3, and then it would extend even further than that. So given this system where x and y are variables, and then a's are the coefficients of x, b's the coefficients of y's, and then c is those constants at the end. As long as the determinant of this matrix is not 0, then our system has a unique solution given by the following. I'm going to write what this is first, and then explain how we get that. So x is going to be given by d sub x over the determinant, and y is d sub y over the determinant. Okay. So again, this d is going to be the determinant of these coefficients. So our x coefficients, our y coefficients, the determinant of that matrix. That's what's going to go in the bottom. the matrix D sub x, it's still going to be a determinant of something. And what you're going to do here, instead of having these x values, you replace them by the coefficients. So that first column is replaced by what it equals. And then the y stays untouched. And then D sub y, same idea. My x has nothing changed, so I still have the coefficients of x. But you replace y's coefficients with the constants. Okay? So it's much easier in practice. It is just an algorithmic process for this. So let's try using Cramer's rule to solve this system. But again, you can use elimination or substitution to find the solution of this. So I'm going to start by finding my matrix D. Okay. So D is going to be the determinant of my coefficients. So I have 3 x's and 2 y's, then 2 x's and negative 1 y. So I just do those coefficients. So the determinant of a 2 by 2, I take the product. So that gives me 3 times negative 1. And then I subtract the off diagonal, which is 2 times 2. So that gives me negative 3 minus 4. The determinant of this matrix is negative 7, which is good because this is going to go in the bottom. I don't want to divide by 0. That's why we need a D to not equal 0. Now to find D sub x, again, it's going to be a 2 by 2 determinant. The y coordinates stay untouched, but instead of x, I replace it by these constants. So negative 4 and negative 5. And then we go ahead and take the product, and hopefully at this stage you don't need me to write all of that out, but that would be positive 4 minus negative 10. Sorry, my dog is walking in the background. So that turns into 4 plus 10, which is 14, okay? So again, all we did is we replaced the x coefficients by the answer columns. Okay. Then to find D sub y, try to keep the system in here for this last one. The x stays the same, but now our y's get replaced by the answer column. So we replace the y coefficients by the answer column. And then we go ahead and take that determinant. So 3 times negative 5 gives us negative 15. Subtract the off diagonal, which is 2 times negative 4, and that is negative 8. So that turns into negative 15 plus 8, which gives us negative 7. Okay. So now our x value is D sub x over the determinant. So that's 14 over negative 7. The x value of my solution is negative 2. My y value is D sub y over D, which it happens to be negative 7 for both. So my y coordinate is 1. So my solution is negative 2, positive 1. Okay. So this idea really stems to any size system you want, not just 3 by 3, but it's the same idea. You find the determinant of your coefficients, and then to find d sub x, you replace x values by the constants. To find d sub y, you replace the y values by the constants. And then d sub z, you replace by the constants. So let's try just one more example of Cramer's rule to again find our solutions, which hopefully you can see this is a little nicer than Gauss-Jordan method because those can involve a lot of fractions. So this one's at least a little bit cleaner in that you find those components, and when you're multiplying stuff for determinants, you're not ultimately ending with fractions because none of these values are fractions, right? So we're going to start by finding the determinant D of this system. So we find the determinant D by using the coefficients of the variables. So the determinant D, I got to copy all these values. So X, our first row is 1, 1, negative 1. Then I use the second row, which is 2, negative 1, 1. The third row is 1, negative 2, positive 3. Okay. And then I want to take the determinant of this, and it should give me just a number. So again, for a 3 by 3 system, I go ahead and I copy my matrix down, and then I copy those first two columns again. Okay. Then I want to go ahead and I want to multiply my main diagonal. So I'm going to start by multiplying these, and I like to put them in parentheses. So 1 times negative 3 times 3 is negative 3. Multiplying those three together gives me positive 1. And then multiplying those gives me positive 4. And then I'm going to subtract, doing the same thing, but on the off diagonals. So multiplying those gives me positive 1. Multiplying those gives us negative 2. And multiplying those gives us 6. So adding those together, that gives me 5 minus 3, that's going to be 2. And then 1 minus 2 plus 6 leaves me with 5. So this determinant is going to be negative 3. Okay. Now I'm going to find all of my d sub x, d sub y, d sub z by replacing that corresponding column with that answer key, that constant, negative 2, negative 5, and 4. So now we're going to find d sub x by replacing the column of x coefficients with the constants. Or you can call it the answer column. Okay. So again, I'm going to cheat because this is a lot of writing. Because we're going to use the same determinant, but again, instead of x, I get rid of those values. And in turn, I go ahead and put these values in. Negative 2, negative 5, and 4. and then I find the determinant of this matrix. So again, I go ahead and I copy my elements down. Let's go ahead and get rid of that so they're all the same color. Then I recopy my first two columns and put them at the end. Then I go ahead and I do my product. So multiplying those together gives me positive 6. 1, 1, and 4 gives me positive 4. And then 3 negatives means overall negative, and that becomes minus 10. Then I subtract the back diagonals. 4, negative 1 turns to positive 4. Negative 2 turns to positive 4. And then the ones I'm just ignoring, 3 times negative 5 is negative 15. So that turns into 10 minus 10, which is 0. And then that's going to be minus 7. So this determinant is equal to 7. So my x solution is going to be this divided by negative 3. And I want to indicate that's d sub x. So I forgot to do that. Okay. Now I just keep repeating this process. So we find d sub y by replacing the column of y coefficients by the constants. Okay. So I'm going to go ahead and I'm going to take my determinant again, and to find d sub y, I get rid of y's column, and then I plug those same constants, negative 2, negative 5, and 4 in. Now I go ahead and find this determinant. So I copy my values down. I repeat my first two columns. And now I go through and start multiplying. So again, I don't worry about ones. So this is negative 15. When I multiply those, that is negative 2. And then that turns or multiplies to negative 8. Then I subtract the off diagonals. So those 3 give me positive 5, positive 4, and then let's see, that would be negative 12. So that will give me negative 25. And then 5 plus 4 is 9, minus 12 is negative 3. So negative 25 plus 3 gives me negative 22. So that determinant is negative 22. Then I have one last determinant to find. We find d sub z by replacing the column of z coefficients by the constants. Okay. So I need to go back up and again get my starting determinant matrix, bring that down here. We are finding d sub z. So I get rid of the z column and replace it with -2, -5, and 4. And then to find this determinant, again, copy everything down, recopy the first 2 columns. Okay. So now we go ahead and multiply. So that's going to give us -4, -5, and then that will be +8. Then we subtract. Starting with these, that will be +2, +10, and +8. Okay. So adding those together, it's -9 plus 8, -1, and then that becomes -20. So this determinant is -21. Okay. So now that we have that, the solution is the following. The x is d sub x divided by d. The y is d sub y divided by the determinant. And z is d sub z divided by the determinant. So going back through these, our d sub x is -7, +7. And then the actual determinant was the very first thing we did. That one is -3. And then that, unfortunately, I can't simplify. It's just negative overall. D sub y, we just figured out, is -22 divided by d, which is -3. So that at least does turn positive. And then d sub z is -21 divided by -3. That one we actually can divide. It is 7. So our solution, the x coordinate is -7/3. The y coordinate is 22/3. And the z coordinate is 7. So again, this is the same answer you would get if you were to use Gauss-Jordan elimination, or if you instead solve this system just normally. But this, I think, is much cleaner than either of those methods because the determinants are much simpler calculations to go through. But again, they all lead to exactly the same answer. They are just different methods. But this works better for higher order systems.